Okay, so let's get started today. Thanks for joining us for today's Physics and Astronomy Colloquium. It's a pleasure for us to welcome Vasily Belokurov from the Institute of Astronomy at Cambridge, where he's currently a professor. And he's also associated with the CCA Flatiron Institute at New York, where he's currently visiting. We plucked him from there to come visit us for this colloquium, and we thank him for coming down. So we like to, the wishes of our speaker, we like to take into account, when they come to visit us. And Vasily has specifically requested that we have a very short introduction for him. So I will pass over all the accolades that he deserves for this introduction, so we can get right to the science, right?
Yeah, perfect.
Okay,
Thank
so,
you,
but I will just say one couple things. So Vasily,
now I regret. Yeah,
okay, got a PhD from Moscow State University, and he moved then to Cambridge. Right? Did I get that right?
Almost got it right. But
okay.
I did my undergrad in Moscow. Then I went to Oxford for PhD, and then
I moved
to Cambridge. Okay. And that's it. It's done.
Okay. Thank you for introducing yourself.
My short.
Let me just say he got promoted very quickly at Cambridge, well deserved. And just let me just say he's one of the leaders in this field that he's going to talk about, if not the leader, of understanding structure of Milky Way galaxy and local group through dynamical measurements of stars in our galaxy. And he's going to tell you all the really, really interesting things that are going on in this field these days. So I'll leave it at there.
Awesome. Thank you very much, Louis. Thanks for the kind words. And thank you guys for coming, and thanks for inviting me. Unfortunately, I won't be able to tell you all the cool things about our galaxy and the Gaia data, because that will take probably a couple months. We only have 3 or 4 hours today, so I'll have to pack it in. All right. So I was going to say, if you don't understand some of the slang I'm going to use, some of the terminology seems unfamiliar, stop me, but no one really does. So, but maybe you can try, and because I don't want to lose my audience straight away. I'll try to unpack. Let me just explain. So to give you at the get-go a small bit of information. Everything I'm going to explain to you about the formation of and evolution of our galaxy, the Milky Way, most of it is really we're discerning it from a very small patch of a stellar field around the sun. So in some sense, there's a big extrapolation going on, but you should keep in mind whenever I'm talking about the data and all the stories that I'm going to tell you how I think we should be interpreting it, I'm doing it from a very local, small volume, extrapolating to the entire virial volume of our galaxy. And of course, you could do it because in galactic dynamics, we use this continuity assumption. And so if you know the velocity of your stars locally, you can then make predictions as to how the spatial distribution will look like. So this is the trick we're using. We're relying on understanding the kinematics to forecast the spatial distributions across the virial volume. So this talk is about the formation and evolution of the Milky Way. And the very first question is, when was that important epoch in the life of our galaxy? And the answer, probably most of you already know it, it happened all very long time ago, billions and billions of years ago. And so that is not surprising. Here's a summary of what we think is happening with galaxies in our universe. Here's redshift, here's time if you want, look back time. And here's the star formation density measured, let's say, on average across the universe. And you can see that star formation is increasing as the time goes. And around 10 billion years ago, it reaches its peak and then subsides. So this is the area of most active growth, of most active merging and transforming across the universe. And so it's natural to assume that that's also the important epoch for the Milky Way itself. And of course, most of this evolution can be explained with a very simple n-body simulation of dark matter structure appearing. And here's a digest of a simulation like that. Here's the number of mergers onto halos of different masses. And here's a halo of the mass of 10 to the 12 solar, which is what we think the Milky Way's dark matter halo weighs. And you see the number of mergers is high at high redshift and then drops around redshift of 2, right? So this transformation from a peaking activity and merging and forming new stars gives way to this quiescent phase, and that backbone of this behavior can be explained just with number of merges supplying the matter for and fuel for the formation of stars. So we think that what the Milky Way, when the Milky Way became the galaxy we know and love, that happened maybe 10 billion years ago. So how can we peer into that distant past? Before we do that, we can ask ourselves what we think may have taken place and in that epoch. And merging and accreting and interacting with other, quite often smaller galaxies can lead to a lot of transformations in the Milky Way. So some of the metamorphoses that we expect to have taken place is listed here, right? So interactions with smaller galaxies can splash, destroy, heat up the disk if your galaxy managed to form a disk. It can also swing or flip or tip the disk, right? So reorient its angular momentum direction. Yeah. Very good question. Yes, these are galactic merges, right? So these are big chunks of matter coming onto the Milky Way, and sometimes not even interacting directly, especially, for example, for swinging or flipping the disk, maybe just flying by, right? So yeah, these are big chunks of matter, not stars. So stars do not typically interact, even if galaxies interact. Galaxies are weird because they're extremely sparse. So when they go through each other, stars don't tend to interact. That's the mystery and the beauty of galaxies. So these interactions can also destabilize the disk. They can induce spiral arms and bar buckling. In terms of star formation, such an interaction can suppress star formation. It obviously suppresses star formation in the smaller galaxy that comes in. It can also promote star formation in the host galaxy. So all these processes can take place. Probably most of these processes did take place in our galaxy. And what we're trying to do now is to look at this archaeological record in the solar neighborhood, in a very small patch of our galaxy, and reconstruct all of this 10 billion years ago. So I think this is quite an enormous task, but it's a lot of fun as well. And the reason we can do this is because the stellar lifetime depends on the star's mass, right? And so stars with sub-solar, less than 1 solar mass, live roughly Hubble time, right? So all the low mass stars that formed 10, 12 billion years ago and are witness to these processes that happen in our Milky Way at that epoch survive to present day, and we can use them to decipher what happened. So that's the trick that we're going to play. All these processes, the details and the outcomes of these transformational processes depend in detail on these things. The accretion history, so when and what fell onto the Milky Way, what were the blocks that were interacting and disturbing and destroying our galaxy, how much gas they were bringing with them, right? Because could we reuse their gas, right? Was it poorly enriched or not? And of course, the geometry and the kinematics of these interactions, that's what's going to set up how much destruction happened after the interaction. And so the idea, again, is to reconstruct now these things so we can deduce what transformational changes took place. And here's a simple animation that explains why and how we can do it. So here's a formation of a stellar halo of a galaxy like our own in this animation. And different colors represent stars coming with one small dwarf galaxy merging with the Milky Way. So if it's the same color, means that the stars share the progenitor galaxy. They fall into the potential well of the Milky Way. They disrupt, and then they phase mix in the field, in the gravitational field of our galaxy, right? And eventually they fill up the virial volume of the Milky Way, creating this colorful mess. But looking at this mess, it's very difficult to say what came from which progenitor, because of course we don't get exactly the stars color coded or tagged for us, telling us from which dwarf galaxy they came. And of course, we will also want to infer when this interaction happened and what was the geometry and the energetics of the interaction. So how do we do it? How do we untangle this mess? And the trick is translating from the spatial dimensions into the dimensions of integrals of motion. So here's a view of the space of integrals of motion. In particular, here is the vertical projection of the angular momentum, Lz, and energy are shown for stars that came with these dwarf satellites. They got disrupted. Their stars are now all over the Milky Way, phase mixing happily into this mess. However, in the space of integrals of motion, the integrals, so they don't change dramatically over the time of the galaxy, they kind of remain frozen where they were deposited into the Milky Way. So you get a very different picture if you can translate into the space of integrals of motion, and you can then decipher the accretion history and unpick which blocks came into the Milky Way. This, of course, was a fairy tale some even 10 or 15 years ago, because we didn't have access to integrals of motion for any appreciable number of stars. Measuring proper motions and distances is incredibly difficult, and that's where Gaia comes in, right? So with Gaia, we can now measure proper motions, and the proper motions are the two missing components of the velocity that we require to build these 6-dimensional phase space information for every star, from which we can then calculate orbits and so on and so forth. So galactic archaeology relies on having access to the integrals of motion, or perhaps just the phase space information locally, to unpick the history of the galaxy formation. In fact, we attempted to do this very early on. So here's one example, in fact, the very first example of doing galactic archaeology and then using chemokinematics, so chemistry and the kinematics of local stars, to infer how the whole thing formed, how the galaxy formed, right? So again, these are very local stars, and here's the eccentricity of the orbits, and here poor man's metallicity, right? So this is a UV excess, and here small numbers correspond to metal-rich stars, and you see the orbits are circular, eccentricity is low, and high UV excess, metal-poor stars, the eccentricities are high, and so they're more halo-like. There was a very tight correlation in this view of eccentricity, metallicity space. With time, the same plane got filled in, and this tight correlation disappeared, right? It's exactly the same plane, but some 40 years later. You can see it's now filled in. There's some clumping going on, but there is no tight correlation anymore. With Sloan Digital Sky Survey data, we actually got even better view of this plane of eccentricity and metallicity. Now this is spectroscopic metallicity, where we decipher the amount of iron in each star by looking at the spectra rather than doing this UV excess measurement. Here you can see now a lot more stars, some clumping. Patterns are similar, but not exactly identical. What's interesting is with time, exactly the same data or similar kinds of data were interpreted very differently. In the first attempt in Egan, Lindenbell, and Sandage paper, this correlation was taken as evidence for the monolithic collapse of the gas cloud from which the galaxy formed. And then later on, some clumping in this space was interpreted as evidence for mergers with the Milky Way of smaller dwarf galaxies coming in. And then some 10 years ago, the same information was interpreted as the existence of dichotomy, duality in the stellar halo. So perhaps there were two channels. The authors surmised that there were two channels of forming stars on halo-like orbits. So I'm going to look at the very similar data again now with Gaia. Right? I have the privilege that the data have become much better. I have the sharpest view of the same data set, and I'm going to give you yet another explanation, right? So it's the same game, telling you a story, making you believe it, and then in 5 years it's going to change. There has been a prediction as to the details of the accretion history of our galaxy before the Gaia data came in. Right? So in this paper in 2013, Alice Deason looked at the stellar halo density profile and made a very brave prediction, right? Where in the abstract, she says, well, looking at the break in the stellar halo density, right? So this is galactocentric distance. This is just the number of stars, and you just count stars in spherical shells. And you see that at some distance, some 20 kpc from the galactic center, the relatively shallow power law density changes into relatively steep power law density. And there is a very obvious break in the stellar halo density behavior. So when she looked at, first she measured it, and then she looked in the simulations and noticed that it can only exist if the accretion history is dominated by an old and massive merger event, right? And so that was her interpretation of this data, claiming that the Milky Way's accretion history is exactly that. One single massive merger event some 8-9 years ago. Right? So of course, with the Gaia data, we have a lot more information now, so we can test this and see what else we can extract. So to look in the stellar halo that contains this archaeological record of the past events, you need to identify stars that were accreted onto our galaxy and are in the halo, so not born in the disk and have very different orbits from the disk. So how do you do this? It turns out it's pretty much impossible to do it cleanly. There is no simple way of extracting a sample of halo stars, right? And so if you're interested in chemokinematic properties of your halo, if you try to carve it out from your data set, you're going to impose biases, selection biases, which will affect any inferences that you subsequently do. So we took a different approach. We decided not to carve out samples of halo stars, but model the entire data set we had. Basically, we had 7-dimensional data set where we had 6 phase space coordinates, so 3 positions and 3 velocity, and then metallicity. And so in that 7-dimensional space, we modeled the distribution with a mixture of Gaussian components. And this way, we didn't impose any strong biases in our analysis, but we could still track the behavior of the halo component, how it changed, because we were really after one simple thing. We wanted to know how the velocity ellipsoid looked like as a function of metallicity, right? So if you look at the distribution of velocities of your stars, we typically call it a velocity ellipsoid. It's assumed to be a multivariate Gaussian. You basically imagine 3-dimensional Gaussian in the space of spherical projections of the velocity, right? So you have VR, v theta, v phi, and you're looking at the velocity components in the space, and you're describing the whole distribution roughly as a Gaussian, and then you can quantify its shape, how flattened it is or how spherical it is with this value called beta, which is essentially a ratio of the amplitudes of motions of the stars moving on orbits around the Milky Way, right? How much of the motion is in the radial direction and how much of the motion is in tangential direction, right? So when the amplitude of motion for a sample of stars is similar, then you have isotropic velocity ellipsoid, and so beta will be 0. That's isotropy, similar amplitudes of motion in radial and tangential direction. If you have preferred direction, for example, if you have radial preference, you're going to make beta much larger than 0. It will tend to 1. And if you have preference for tangential motion, it will go negative, and it can go to negative infinity. So what we noticed immediately is that the shape of the velocity ellipsoid depended very strongly on the metallicity of the stars we were looking at, right? So the metallicity is shown here, and you can see that there's a swift switch in the shape of the velocity ellipsoid. So around here, where the stars are metal poor, we have something that is vaguely consistent with stellar halo being built up from multiple accretion events of smaller dwarfs coming from different directions and mixing and phase mixing, giving you roughly isotropic velocity ellipsoid. But around here, at the higher metallicity, we had a very different and very distinct behavior, that we had a one preferred direction. We had the radial preference. So it seemed to indicate that many stars came in radially and had a head-on interaction, collision with our galaxy. It's a very different behavior in 2 different metallicity ranges. So just to show you how these 2 distributions might look like, so here's the metal poor selection, and here's metal rich selection, and I'm showing you radial velocity and tangential velocity. And so here's the isotropic distribution, roughly spherical projection in this space. And here, very stretched radially distribution. So we named it a Gaia sausage because it looks like a sausage. And that name we kind of stuck, and we keep using it. There's a much more beautiful story, and the name is it's sometimes called Gaia Enceladus, with some Greek mythological fairy tale attached to it. We were just very simple-minded and had a very descriptive name to the structure we saw. So the sausage refers to a strong radial anisotropy in the local velocity field for the stellar halo. And so this behavior was a giveaway that something very dramatic happened in our galaxy. So we think, looking at the velocity ellipsoid locally, that a massive, probably single massive merger happened some 8 to 10 billion years ago. And we have various pieces of evidence supporting this hypothesis. We think it's single because it's dominant, and there's nothing else in the local stellar halo field. If you look at the number of stars, they're shown here in the right top corner of these two velocity slides. As you can see that the metal-rich-ish distribution of stars that is stretched radially dominates the metal poor by, an order of magnitude. So most of the stars are in this radially anisotropic component. So we estimate that of order of 2/3 of the local stellar accreted halo is in this component. So it's a really dominant, most massive contribution. We can estimate the total stellar mass of the progenitor galaxy. The galaxy is destroyed, it's no more, it's phase mixed all over the Milky Way's virial volume. But because we know the metallicity of the stars, we can use something known as metallicity on the y-axis. Stellar mass here is actually luminosity relationship. And you can see that if you take local nearby dwarf galaxies and you plot them in the space of metallicity and stellar mass, there's a nice correlation between these two properties. And this correlation in simple terms appears because of the stellar feedback, right? So the energetics of the stellar feedback is universal. It doesn't depend on the galaxy where stars are born and then push out the gas as they explode. But of course, the restoring force that will then help the galaxy to bring back the gas that it just pushed out to keep forming stars from it depends on the gravitational potential of the galaxy. So all galaxies push out stars with the same energy, but then the ability of the galaxy to reaccrete the stars so you can form subsequent generation of stars will depend on its mass. What it means is that the dwarf galaxy will struggle to keep the gas and reuse it for self-pollution and self-enrichment, while massive galaxies will easily reuse the gas. So that translates into the increase of the rate of star formation for the massive galaxies and suppression of self-enrichment and star formation in dwarf galaxies. So that establishes this luminosity metallicity relationship. So we can use it. We measure the typical metallicity of the stars and the sausage structure. So we can just read off this plot what the total stellar mass of that progenitor dwarf galaxy that is no more, right? It's destroyed 10 billion years ago, but we can easily tell what its mass was, right? So it was probably more than 10 to the 8 solar. Yes. Yes, 0 is solar, -2 is 100 times less than solar. Yeah, thanks. Sorry about. And then final piece of evidence, we can compare to the numerical simulation or simulations of galaxy formation and ask ourselves, if we look at these simulations that we know how to run, we don't know maybe how to model the gas dynamics or star formation physics properly, adequately yet, but we can at least ask ourselves what the properties of the accretion events were in the Milky Way type progenitors in the simulations, because that's just collisionless dynamics that we know how to do. So here in this plot, I'm plotting the accretion redshift, right? So again, 2 is roughly 10 billion years ago. And for every dwarf galaxy that comes into the Milky Way in the simulations, I can measure its the shape of its velocity ellipsoid around the sun today. So kind of doing what I'm doing with Gaia, but in the simulations, but splitting the debris that's left behind after the galaxy is disrupted by the progenitors, right? Because I have the tags in the numerical simulation. And that's what is shown here as curves, right? So there are 3 different curves for three different beams of mass of progenitor galaxy. Blue is low, green is intermediate, red is the most massive. You can see that only the most massive dwarf galaxies can disrupt and yield highly radially anisotropic velocity ellipsoid around the solar location at redshift 0. So today in these simulations, and typically these are accreted around redshift 2, so of order of 10 billion years ago. So these are different pieces of evidence that we now trying to assemble, interpreting these Gaia data, again, very local stellar velocity field. So you could do it much better with more sophisticated numerical simulations. Here's one such suite of simulations. This is our Riga project led by Rob Grant. And you can see these model mock Milky Ways are shown here in face-on and edge-on projection. And there are roughly 30 of them. They vaguely look like a Milky Way galaxy. Well, there is a disk. Maybe it's a bit too thick and too hot, maybe a bit too red. But there's some ongoing star formation, excuse me, some spiral arms, some bars. So for all intents and purposes, this is our mock Milky Ways. So we can look at these Milky Ways, just like we did look at the local stellar field in the Gaia data in our own galaxy. So here's the data for the velocity field in the Gaia data set. Again, radial velocity, azimuthal velocity aligned with the rotation. You can see this big clump of stars that are all rotating with roughly 200 kilometers a second. This is the disk of our galaxy. And underneath, we have 0 azimuthal velocity, not much spin, but with huge dispersion in radial direction. Is this remnant cloud of stellar debris that were left behind by this massive merger. So this is the data. And here's a set of examples from the Riga suite. There are 4 galaxies here. And I'm showing exactly the same projection of the velocity field for all stars. And because this is the simulation when I can peel off the stars that I don't need the stars that formed in situ. So the Milky Way disk, I can get rid of it, right? So I can just switch it off. And so the intermediate panel is showing just the accreted stars. And you can see that the velocity ellipsoid, the velocity distribution of the stars that have been accreted in this mock Milky Way has a variety of shapes, from very radially stretched to almost isotropic to tangentially anisotropic. So strong radial anisotropy, strong tangential anisotropy. So there is a huge variety of behaviors dictated by the details of the accretion histories in these galaxies. So what we can do now, we can just select those example Milky Ways that look like our data and then ask ourselves, how did they end up having this sausage-like structure in the velocity space around the sun? So we quantify the velocity ellipsoid with this parameter beta, which is the ratio of the radial amplitude to the tangential amplitude. And remember, 1 is radial anisotropy and around 0 is isotropy. And here on the x-axis is a fractional contribution of this radial anisotropic component to the overall stellar halo, right? So in the Milky Way, we think it's at least 2/3, maybe more, and it's highly radially anisotropic. So this is the corner of this space where our observations, the Gaia observations, lie. And you can see that when we compare to the Riga suite of more galaxies, roughly 1/3 of galaxies have a similar kind of behavior of the local velocity field, right? So they all have a similar sausage-like structure. So when we take these galaxies and plot the accretion history, this is cumulative mass assembly. So time starts from the Big Bang, where it's 0, and goes to roughly 14 billion years, so present day. And this cumulative mass assembly reaches 1 at redshift 0, or present day. And so red curve is a stack of all the Milky Ways that sit in the top right corner. And the blue curve is all the Milky Ways that are the rest, that don't have a strong radial anisotropic metal-rich component around the sun. And you can see that all these Milky Ways had a very rapid formation period, right? So you have to count, if you want to look back time from here back to here, so some 10 billion years ago, they all undergone this fast, rapid assembly period, and then will subsequently evolve in more quiescent mode, while the rest had a different mass assembly history. Right? So again, pointing at the same pattern and telling us that indeed the presence of this highly radially anisotropic structure in the velocity space is actually a very powerful and important marker we can use to deduce the past of the Milky Way. Of course, in the simulations, you can do a lot more, because you can say, well, now I know that something happened in my mock Milky Way 10 billion years ago. What exactly happened? So you can ask what sort of building block, or what sort of dwarf galaxy came in, how massive it was, and so on. So if you select galaxies that have this velocity sausage in the simulations, and then plot the accretion times, so the merger time is on the y-axis and the stellar mass on the x-axis, you can see that they're all pretty massive. This is stellar mass, so typically 10 to the 9. So this would be of order of LMC today. So the LMC is the largest satellite of our galaxy that we see around us now, and they all came between 7 to 11 billion years ago. So again, you're starting to, just from very simple measurement of the shape of the velocity ellipsoid and the typical metallicity of stars that are moving on this almost needle-like orbit in and out of the galactic center and back to the, the epicenter, which is around 20-30 kpc from the galactic center. Knowing the orbital shape and knowing the typical metallicity, you now have built a whole story of Milky Way being smashed into by a massive dwarf galaxy. And I told you when, how massive it was, and I can keep going trying to unpick this story. Sorry, was there a question? No. Okay, but do ask. There's a small pause here because I'm just summarizing what we've learned, right? So we could now look at this data in many different ways and start testing this hypothesis of single massive merger at a particular time. And so there is now a consensus, there is now a convergence in terms of the estimates of the accretion time. So you can measure it different ways. You could compare to the zoom-in simulations, just as I did right now. You can look at the actual ages of the stars. So stellar ages are tricky. They're not easy to come by. Only a handful of stars have reliable ages measured. But even with this handful, you can select those that belong to that dwarf galaxy or are now in this debris cloud and say what is the cutoff age, right? So the cutoff age will correspond to the epoch of the life of that dwarf galaxy when it stopped forming stars, right? As the dwarf galaxy comes into the Milky Way, its gas is removed through round pressure and its star formation activity is suppressed, right? So the stars cannot form, the galaxy will then fall into the Milky Way and disrupt. So there should be a cutoff age. And so if you measure this cutoff age, it also gives you a number of order of 8 billion years ago. You can model the chemical enrichment history of the galaxy, right? So you can look at the chemical properties of the stars in this debris cloud, and you can say, for example, acquire accurate measurements of alpha abundances and iron abundances. And alpha elements are produced for predominantly one channel, core collapse supernova, while iron is produced for two different channels, right? You have core collapse and type 1a supernova. Because of these different channels contributing on different time scales, that gives you a handle on the details of star formation history in one galaxy. If you can link the stars together, right? That's the trick. The stars are now all over our sky. We are doing something really simple, but really powerful. We are connecting them based on their orbital properties. We can then link all the stars that span 2 or 3 orders of magnitude in terms of their iron abundance, right? We connect them together and we say the stars that are metal poor exploded, and the gas that was enriched was then reused by the stars that are slightly more metal rich, and so on and so forth. And from this sequence, we can reconstruct the history of this galaxy. And this gives us an independent measurement of the star formation history that, again, agrees with this estimate. And then finally, you can look at the ages of the stars in the Milky Way that was splashed or heated up by this merger. That's something now to do with how the Milky Way withstood that particular head-on collision, right? And so because that was a single most important merger in the life of the Milky Way, you can just select stars that were born in the Milky Way and now on halo orbits, and ask yourself, is there a particular cutoff in age distribution? And indeed, there is also a cutoff in the distribution of ages of the in situ Milky Way stars. And it again corresponds to this particular period in the life of the galaxy. And we have a very good idea of the total stellar mass through a number of measurements. You can look at the number of globular clusters that were brought in together with this dwarf galaxy. You can again follow the same idea of modeling the chemical enrichment that gives you star formation history, which you can integrate to give you total stellar mass. You can do a very simple thing. You can just say, what is the total stellar halo mass of the galaxy? Because that should be the upper limit for the mass of that dwarf galaxy. And again, there's an agreement. It's roughly just under 10 to the 9 solar masses in stellar mass, right? So stellar mass is easy because you see the stars, you can count them, you can extrapolate. What is unclear, how much dark matter exactly that galaxy brought in and how much gas it brought in. And that's something that we're still working on, and it would be important to understand because we would like to know if that gas was reused by the Milky Way for subsequent star formation, and whether that dark matter that that galaxy brought with it actually changed the distribution of dark matter in our own galaxy that could then dictate the subsequent evolution of the Milky Way. So in the remaining time, I'd like to talk about the response of the Milky Way. How much remaining time remains? Okay, cool. Well, I'll try to go through some of this and see how far I get. So as Gaia was releasing its data, in particular the data release 2, every data release actually comes with a bunch of science demonstration papers where the Gaia Science Consortium shows off the properties of the data, how beautiful it is, how powerful it is. You know, now we can measure proper motions. Now we have great parallaxes, so we can move from apparent color and apparent magnitude of a star into absolute magnitude, so luminosity, intrinsic luminosity, and say temperature. And there was a paper exactly about that by Karin Babusio that built a whole bunch of different Hirschsprung-Russell diagrams. So color, temperature, and then absolute magnitude, the luminosity, because they indeed look very beautiful. And you can do it for various samples of stars. And this particular plot from that paper is for stars with high tangential motion. And this high tangential motion is with respect to the sun, right? So these stars move very different from the sun's motion. So they're not moving with the sun, so they're not rotating in the disk. So essentially, these are the stars that are in the halo, right? So they're not disk stars. And when you plot this Hirschsprung-Russell diagram, you see the familiar features of main sequence, turn-off, red giant branch, horizontal branch. But what you see immediately is that this density field is split into two portions, right? There is a clear divide, and there are two sequences going through the entire range of magnitude. So there are two sequences, so there are two halo populations, the red one and the blue one. And here's the kinematic view of the red and blue population, right? So the red halo population and the blue halo population turned out to have very different, similar but distinct kinematic properties. So here, projections, Cartesian, it's not spherical, projections of the velocities. V is now, because all these stars are more or less around the sun, right? So it doesn't really matter. So V is aligned with azimuthal velocity, right? So it's in the direction of the rotation of the sun. And then U and W are the two other components, so radial and vertical components of their velocity. So this is kind of how fast they're rotating, and that's the two other velocities combined together. And so the solar local standard of rest here in this heliocentric view is at 0. So local standard of rest is of order of 240 kilometers a second. So minus 240 in this view will be halo, which will be galactocentric, reference frame 0, right? So all these stars have roughly 0 azimuthal velocities because they're halo stars. And you can see that this red population actually many stars have 0 rotational velocity, but there is a huge wing that stretches towards the disk. So the disk is excised here, carved out. It will be here. So this red population is essentially a wing of the disk population, while the blue stars don't necessarily want to be rotating. and they have higher energies overall, right? So they stretch up further, right? So immediately, by looking at the Hirschsprung-Russell diagram and understanding the connection of the red population to the disk, you know that this is metal-rich population that was formed in the Milky Way. And essentially, this is dynamically heated disk. So that merger came and destroyed some of the disk, heated it up, changing the orbits of the stars from rotating circular-ish orbits into much more radial halo-like orbits. You could also model this Hirschsprung-Russell diagram with throwing a bunch of isochrones, assuming mass function or luminosity function, and producing a model of this density distribution. And from that, you can extract ages because you have good idea of distances to do that. And it turns out that while the chemical properties are extremely different, so the blue population is very metal poor. Again, this is Fe over H, so iron abundance with respect to solar, where solar will be 0, and this is 100 times more metal deficient. Right? So the blue population is very metal poor. These are primitive stars. And as I told you, there's this mass metallicity relationship. So they were probably born in a low mass progenitor galaxy, while the red stars are not far off solar, actually, right? These are metal rich stars. So dwarf galaxies cannot self-enrich to this value. But when you look at the ages, so this is the age histogram, right? The blue histogram and the red histograms are on top of each other, and they're all very old. So they were born roughly around the same time, but into very different environments. And there is a causal link between these two populations. The blue stars were in this unfortunate galaxy that smashed into the Milky Way. They got scattered all over the Milky Way proper. And the red stars were living in the Milky Way at the time. They were in this prehistoric primordial disk of the galaxy, and they were heated up by the interaction onto halo-like orbits. So these are signatures of this response of our galaxy to the merger. And here's probably a much clearer view of that of what happened, because here we have access to the age. I said ages are difficult. These are not the best ages in the sense that these ages are inferred by modeling color magnitude diagrams. So these are so-called isochronal ages. They have large errors, especially when the age grows beyond 8 gigayears. But nonetheless, you have some information in the behavior of the age, which is the x-axis, and the azimuthal velocity, so the rotational velocity in the galaxy. Again, these are local stars, and I'm making a story about the whole galaxy. So this is rho normalized density plot for metal-rich stars. So all stars are born in the Milky Way because they're metal-rich. So we're looking at the Milky Way. We have the idea of the ages, and I'm doing rho normalization. It means for every velocity on the y-axis, I am counting, I'm integrating stars along the x-axis, and I'm dividing by that, right? So I'm picking up kind of where the distribution of ages peaks for every value of velocity. And you can see that if you look at the high rotational velocity, what we think is typical for the disk, there's a whole range of ages. Disk stars have been forming for, we think, 8 to 9 gigayears, and you can see that. But if you look at low angular momentum, low spin, or even retrograde, rotating in the opposite direction, there's this bar, there's this narrow distribution here. All these stars were born in a particular age in the Milky Way. And it makes sense because that's how they got to be on these orbits. They born before the interaction, and the interaction kicked them up. And these are just one-dimensional slices of this distribution, showing you that if you look at the metal poor stars, the blue curve, and metal rich stars, and both samples have no rotational velocities, so V phi azimuthal velocity is less than 0. You see that they are synchronized. They have this cutoff value around 9–10 billion years ago. So this is a Fisher-Price view of the same density distribution. We think that there is a population of stars that were born early in the Milky Way and got splashed out. And as they were splashed out during that phase, and subsequently thick disk with small azimuthal velocity forms, and eventually the disk settles in the cold thin disk as we know it, right? So you see this kind of chevron structure as the disk grows and becomes cooler and thinner. The most important thing here in this whole story is this causal link between the accreted debris and the splash population, which is the in situ population. It gives us a way to actually constrain the dynamics of the interaction, because you can imagine the more massive the dwarf that comes into the Milky Way and plunges through the disk, the more destruction it will do, right? So from kind of the energetics and from the amount of mass in the splash population, we can tell how massive that dwarf was and how it interacted with our own galaxy, right? So that's what we want to use this splash population for. I'm going to skip this plot, although it's very nice. So far, I've been talking to you about very local view of our galaxy and then making extrapolations, wild extrapolations to the entire virial volume. Of course, with the simulations, I can look at the entire galaxy, and just to show you what all these populations look like in numerical simulation. So here's a slice in XZ, the perpendicular to the disk plane of a model galaxy. So the black contours is the density distribution of the disk, and then the blue contours are the accreted stars. So they fill out the stellar halo. And this splash that is produced by interaction of the prehistoric Milky Way's disk with the incoming massive intruder is this red distribution. And you can see it's much smaller in extent compared to the accreted halo. It looks more like a puffed up bulge, if anything. And here's the data view where we're trying to identify this in situ splash population. So this is done with Gaia RR Lyra, where this is modulus of Z. So that's why you have just 1/4 of this view, but you can imagine it's a spheroidal-like distribution. These RR Lyra are very distinct from the RR Lyra we find in the accreted halo. They're all metal rich, more metal rich than the accreted ones, and they sit in a very particular zone, not far off the galactic center. So this splash population is very limited to 10-15 kpc. It contributes a lot in the solar neighborhood, but beyond that, not much. Just in the few last minutes, I want to tell you about something that is not to do with the data, but what we've encountered trying to decipher the data. And we encountered some new, previously poorly known or not understood at all behavior. And that was a lot of fun. So if we knew the geometry and interaction of the interaction and the kinematics of the interaction, we can then predict exactly what happened to the Milky Way. So how do we decipher that? So we need to reconstruct the orbit of the progenitor galaxy that smashed into the Milky Way. So when we tried to do this, we quickly realized that it's very difficult because the orbit of a massive satellite that comes into a Milky Way-like host is going to evolve dramatically. And we know that because there is dynamical friction acting on a massive body that is plunging through a sea of particles of much smaller mass, right? So if you have a sea or sand of gas or dark matter particles, those will be deflected by the massive body. The orbits will be deflected, changed, and they will start piling up behind the massive body, forming a wake. And this over density, this wake structure will tug on the massive body, slowing it down. So typically, this dynamical friction phenomenon will lead to the massive body changing its orbit. It will become more circular and it will shrink. So the massive body will spiral down to the bottom of the potential well. That's all based on the paper by Chandrasekharas some 80 years ago. And we do see this, right, in simulation. So here's 3 different satellites. So the mass ratio of the satellite to the host is shown here. And there are 3 curves because we start them with different angular momentum. So here is circularity, initial circularity, 3 different colors. Distance, how the circularity changes and how the satellite loses mass. And we just do it for 3 different mass ratios of the satellite to host. And you can see that indeed, all the satellites plunge in and they do become more circular. And you can see that because the amplitude variation between pericenter, the minimum distance, and the apocenter, the maximum distance, start to decrease, right? So the difference between peri and apo disappears over time. So the orbit becomes more circular. And you can see it when you plot the circularity, right? And so that does happen. And then we realize that something else happens, completely the opposite effect happens. So here's exactly the same plots showing you that the reverse can happen. These are the same mass ratios. Everything else is the same. The only thing I changed is this gamma, and gamma is telling me how dense the host and the satellite is. And so this is slightly denser. Sorry, this is the denser one, gamma 3, so the denser one, and this is slightly less dense one. And you can see that instead of becoming more circular, most of these cases actually lost their circularity. They lost their angular momentum, becoming extremely radial. So what turns out is possible that massive satellites, when they come in, they lose their the dynamical friction acts differently, and they lose their energy and angular momentum, becoming extremely radial and ending up smashing head-on into the Milky Way, right? And when we look at what causes this, it turns out that what's important is the self-friction of the host and the satellite. I'm wrapping up, trying to wrap up, trying my best. So the satellite loses material, and the debris will torque the remnant core. But what happens with the host is very interesting too. The host, so the Milky Way proper, decouples into a dense inner part and the remainder, the outer part. And the dense inner part will start swinging around in response to the infall of the massive satellite, kind of sloshing inside, and it will be torqued by its own outer part material. But because of this self-friction and because of the motion of the inner part of the host, this very different phenomenon that takes place, right? So the satellite, instead of circularizing its orbit, sinks very quickly on extremely radial orbit instead. And in fact, this happens when not only when you have a massive enough satellite, it doesn't happen to light satellites. What's important is the density of the matter inside the host. And the typical density that we're considering here is what you expect for the inner parts of an FW profile. So we think that this phenomenon takes place in most galaxies. When a massive satellite comes in, it actually doesn't circularize, it radializes. And that's very important to understand what happened to the Milky Way, how that interaction proceeded. But it's also important when we want to understand interactions in other galaxies, right? And for example, it's important if you're interested in what happens to the supermassive black hole that would live in the massive galaxy that comes into the bigger host, right? It disrupts, it drops its black hole that lived in it. And we typically assume that then the two black holes will come together and eventually coalesce and merge. But of course, if the interactions end up, the final phases end up radializing the orbit of this massive galaxy coming in, when it delivers the black hole, it delivers it on a very unfortunate orbit that is not actually helpful for this black hole to experience dynamical friction and sink to the bottom and meet the other supermassive black hole there. So for example, in the Milky Way, if the radialization took place, and we think it did, just looking at this Gaia sausage structure, we know all the stars on almost radial orbits. So yes, it did happen. So if that galaxy had a supermassive black hole in it, and it's probably our best candidate for a massive black hole, apart from the one that we have in the galactic center, that black hole ended up on an orbit that is actually very difficult to shrink and make that black hole meet our own. So that black hole may be still wandering somewhere in the inner galaxy. Right, so if you're interested in how this orbital radialization of massive satellite happens, please read this paper led by Eugene Vasilyev that just been published in a couple of months. I just have one more thing, but I probably will leave it not to tire you out, and we can talk about it later with those who are interested. What I'm gonna conclude with is the things that we've deduced with these small data limited to the solar neighborhood, but very accurate, very rich data set. We've been able to reconstruct the whole sequence of events, of transformations that Milky Way underwent very long ago in the distant past. So we know that its disk was heated. We know that the stellar in situ stellar halo was formed. Probably its disk was also flipped, tipped, and that's the part that I can explain why we think so. Later, the disk transitioned from this turbulent thick configuration to the thin, but that happened after the event finished and the activity subsided. Probably bar may have formed. Again, there's some evidence for that. The questions that arise that we haven't fully answered are listed here, and that's something that is related to this particular accretion history. So this dominance of one single massive merger some 8 to 10 billion years ago. So there are some questions that are important for us to understand the formation of the Milky Way. So what was the chronology of the event? So when in the life of the Milky Way it happened? Was Milky Way already, did it already have a thick disk? How big it was, and why the transition from thick to thin seems to coincide exactly with the end of that event. Is there causality, or that's just a coincidence? How much gas and dark matter there was? What happened to the gas? Was there star formation burst associated with this interaction? What happened to the black hole? And things that we're working on now and interested very much in understanding where the dark matter ended up. That dark matter, all the dark matter that was brought in by this massive satellite, but also the dark matter that was being accreted onto the Milky Way around the same time. And there are other detailed questions. For example, if we think that the mass assembly peaked 10 billion years ago, does this also imply that the assembly of our entourage of satellites also was shaped by that particular epoch? So were there many dwarf satellites accreted onto the Milky Way around the same time, or co-accreted with this big dwarf galaxy? And I'm very happy to talk about any of these later. And thanks very much for surviving this. Did you unscrew it? Or? Oh yeah, yeah. You can just scream.
The Zoomers. Oh, okay. So right. Okay. Thanks, Vasily, for a great talk. So we have time for questions. Peter.
Yeah.
Actually, can you repeat the question for the people on Zoom?
Yes. So the question is, what's the extent of the data set from Gaia spatially, from which we are doing all this detective work? It's not, I mean, most of the studies that to do with the data that I showed are limited to between 2 to 3 kpc, kiloparsecs from the sun's location. So you can imagine a sphere with radius of 3 kpc. The bulk of what I've talked to you about is based on the stars in this region. Of course, we then, say it again? You mean like the spiral arm? Well, because I'm looking at the halo stars, they're not really in the disk. So they travel through this region, but they don't live here very long. So they just pass. And because most of them are actually radial orbits, they pass very fast, either in or out, right? So they just wishing by, right? And we catching them. And because Gaia is so precise, we actually can see exactly where they go in and where they've been. But yeah, it's very small region. Of course, once we've done all this work, we asked ourselves the question, okay, that's all very nice. We are extrapolating from this small region. Can we see this whole, because there should be a gigantic debris cloud left behind this event, after this event. And so you could trace it through a much larger region with our LiDAR, and we've done that. And we show that there is a coherent cloud of stars that is probably 40 kiloparsecs across, so gigantic cloud. And the stars are all moving in this radial sense throughout this cloud as its phase mixes. So this can be done with our LiDAR, and there's very beautiful work led by Juliana Yurio that uses our LiDAR to map out this structure. Yeah, so some work is now possible outside of solar neighborhood, but most of it has been so far inside the solar neighborhood.
Other questions for Vasily? You can hear me with this. Okay, can you condense it to less than a minute? Okay, well, you know, all his answers take an hour,
Just
so,
say yes
so try
or
your
no.
best.
Yeah, I promise. Yeah.
Once again, can you repeat?
Yes. Yeah. Cool. Yeah. So the question is, I compared the progenitor galaxy to the LMC, to the Large Magellan Cloud. Maybe the more correct way to say it is in terms of stellar mass. So it's similar in terms of stellar mass. Of course, that galaxy formed as many stars 10 billion years ago, and LMC only managed to form these stars, you know, over Hubble time. So the comparison is not very fair. But the LMC is massive, right? We know now that it's more than 10 to the 11 worth of dark matter. So it's exactly in the regime where we expect this radialisation to happen, right? And so we already see the Milky Way starting to do what I just described to you. The central parts of the Milky Way now have decoupled, and they're moving with respect to the outer parts of the Milky Way. The Milky Way is now in this sloshing motion, responding to the infall of the LMC. This has been detected. And because we know what it will lead to, this is the one important ingredient for the satellite to violently and quickly radialize. So we're already starting to see this to happen. So this probably will lead to very fast radialization of the LMC. It takes basically, in simulations we look at, a order of 2 to 3 maximum radial periods. So the LMC just had one passage, probably 1 and a bit, and it should radialize very quickly. And then the disruption happens very fast, and the plunging head-on happens very fast subsequently. Yeah. So, but we already see it happening in the response of the Milky Way to the LMC.
I can ask a quick follow-up. So in the Riga simulations, you showed that there's a lot of these systems have
1/3 approximately.
Inferred approximately, but you have the dark matter mass for the hosts of those things, right? So I mean, you kind of know. Although, what's the range of those things? What's the range of the dark matter?
Of order of 10 to the 11.
Okay, so
total.
so you kind of, so I mean, is it fair to say that that's the thing? You know, that the thing that we observe is 10 to the 11. You know, and that's it.
Probably has brought 10 to the 11 worth of dark matter. Now the question, where this dark matter is and in what configuration it was done, because that's an interesting question, right? So what's the shape of this additional dark matter contribution? And so that is still debated. And there was a paper a week ago on kind of tilt in the dark matter distribution that because the orbit is clearly misaligned with respect to the disk, then you create this kind of a misaligned strange component in dark matter. It's maybe only 10% locally, but it's enough to make, you know, interesting things happen to the orbits of stars. But I have some other things to do with that that I could talk about later with those who are interested.
Any other questions for Vasily? Okay, so if not, let's thank him again, and he'll be around all day tomorrow if anybody wants to follow up.